Okay, we've talked about conditional mass functions for discrete random variables, but now for continuous variables, the natural analog to that is the conditional density. And we can get the conditional density in much the same way as before. In fact, it's pretty straightforward in the continuous case to get a conditional density, as we can express it in terms of the joint density and the marginal density. Okay, so conditional densities. So if a pair of random variables have a joint density, write it as f sub xy, then the conditional density or the conditional distribution, I'm sorry. The conditional distribution of y given x has a density. And the way that we can derive this is in much the same way that we've derived previous cases where we say, well, the variation of y given a specific value of x, well, this is the per unit variation probability that y is within some infinitesimal dy of y, given that x is equal to x, divided by the infinitesimal dy. I'm sorry. Given that x is really close to within an infinitesimal dx of x divided by dy. Well, this is the joint probability divided by dy times the probability that x is close to little x. And now we just use, we can just put this in terms of things that we are already familiar with. So the top is exactly f of x, y, the joint density at xy, dx, dy. The bottom, we already have a dy there. And this is exactly the marginal density of x, dx. So the dx's and the dy's cancel, and what we're left with is the joint density of x and y divided by the marginal density of x evaluated at the conditioning value little x. So this looks exactly like the Bayes rule or the Bayes formula for conditional probability, except we're instead of having probabilities, joint probabilities of events, we have joint densities. And conversely, just like we had the law of total, or the multiplication rule for conditional probabilities, we have that a multiplication rule for conditional densities. So if we have the conditional density of y given x, and we also have the marginal density of x, then the joint density of x and y is just the product of the marginal times the condition. Okay, so now let's look at an example involving waiting times and exponentials and gamma. So the exponential gamma example. Okay. So we're going to assume a large population And W is going to be the waiting time before an accident occurs. So let's assume W is exponential. We're going to assume that W is exponential. I'm sorry. Let's first assume we have a random variable lambda, which has a gamma random which is a gamma random variable with parameter R and beta. And then we're going to define the conditional distribution of W given the value of lambda as exponential lambda. So the conditional distribution of W given this value of capital lambda is exponential, okay? So by the previous multiplication rule, the joint distribution of W and lambda, right, is F, the marginal of lambda times the conditional of W given lambda. Well, the marginal of lambda is gamma R beta, so it's beta to the R over gamma of R, lambda to the R minus 1, e to the minus lambda beta. And W given lambda is lambda e to the minus lambda W, just exponential lambda. And so this is equal to beta to the R over gamma lambda, over gamma R, lambda to the R, e to the minus lambda W plus beta. So what's the marginal density of W? So in other words, if we just get rid of the random lambda, what is the distribution of W? So we have to integrate out. So this is a case of two random variables that are independent, that are dependent on one another. So we have to integrate out lambda from the joint so this is integral 0 to infinity, beta to the R over gamma of R, lambda to the R, e to the minus lambda, W plus beta, d lambda. So we're treating W as fixed and lambda as the variable. So this is beta to the R over gamma to the R integral 0 to infinity lambda to the R e to the minus W plus beta times lambda. So this kind of looks like, does this look like a gamma distribution? Well, not necessarily, but if I put a beta plus W to the R plus 1, and a gamma R plus 1, top and bottom, then I have something that kind of looks like a gamma density. With parameter r plus 1 and w plus beta. So this integral is 1. And what I'm left with over here is I have ratio of gamma r plus 1 over gamma r, which is r, to the beta r over beta plus w to the r plus 1 for values of w that are positive. So that's the marginal density. And how do we reverse engineer? Let's say we observe W, the waiting time, but we don't know lambda. So we want to know what is the conditional density of gamma given, or of lambda given W equal to a specific value. Well, for this, we can use effectively the Bayes rule, right? So it's the joint density, which we know, divided by the marginal of W, which we just calculated. So the joint is the joint is here. Joint is here. Divided by the marginal, which is here. So this cancels. We have R gamma R. We have an R here and a gamma R here. So that's going to be gamma R plus 1. We flip the beta plus the beta plus W to the R plus 1 up top. And we have lambda to the R e to the minus W plus beta lambda. And this is for positive values of lambda. So what does that look like? That looks like the conditional distribution of of lambda given W is gamma with a shape parameter R plus 1 and a rate parameter beta plus W. The original rate parameter beta, right? So look at how we started. We started at R beta and we update to R plus 1 beta plus W. So it's the shape gets updated by the sample size, the addition, we added one observation, and the rate gets updated by adding the additional waiting time that we observed. So that's an interesting update, and that has to this is a very common what's called a conjugate family in Bayesian statistics. And this type of a setup is very common in Bayesian statistics where we specify, so this parameter here, this is called a prior. And given the parameter, we define the distribution of the random variable of interest as 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 a conditional distribution given the random variable lambda, and this is called the posterior. This is the posterior of lambda given the data, right? W is observable, lambda is not. This is the prior for lambda. So that's the terminology you'll see in Bayesian statistics. And this is the machinery that we use to do those calculations.